this video we'll talk about our induction options, so carburation, injection, and we'll start at the basics. So this is the intake manifold of an 821 block. So it's the original cast iron intake manifold. The exhaust has been cut off. You can see this is an 821 block because it doesn't have the Siamese ports, so it has separate ports for each cylinder. This is quite a special manifold. This is a cast aluminium manifold made by Valerio Leoni in Italy, and as you can see, this bolts to the head like this, and it is used for twin downdraft DCNF Weber carburetors. And then what we can see here is the process of designing an intake manifold for twin DCOE Weber carburetors or injection. And this is the first one that I made. It doesn't fit at all. It bolts to the head, but it's way too long. The exhaust doesn't clear. This is a second iteration. It's much shorter, but it has an S shape. It doesn't really clear the exhaust either. Then we have some evolutions which we use to raise the intake a little bit. These are all 3D printed in PLA, by the way. So the manifold is completely designed in Fusion 360, so completely CAD/CAM design. So now we are coming closer to the end. This will fit, but the clearances are a little bit tight. Now we're coming to here. We have a little bit variation on the actual flange shape, but that doesn't really matter. It has evolved from this as well. So when we bolt this on, we can have 2 Weber carburetors, and it will clear the exhaust, it will clear a tubular manifold, it will clear all the coolant pipes, and we can bolt this straight on. And now there's one variation more coming, and that will be the final variation for my engine, which will have this flange a little bit raised, so I get the trumpet straight out, because I'm using electronic fuel injection and not carburetors. If you're using carburetors, we have to have some angle to this, but isn't too steep, because otherwise the float bowls will fail. So this is, I think, 3 degrees back slanted from the engine, and it's perfect for carburetors. So this is the complete design. Now I'll show you the final manifolds bolted to the engine, and we'll talk a little bit more about it then. So this is the design that I made in Fusion 360 for our intake manifolds. This is the shape that I came up with. So we have 2 separate manifolds that go up, and then the throttle bodies are at an angle, because they can be. It will make sure that there's a little bit more clearance for the coolant tubes. On the bottom we have bungs to have vacuum pickups to go to our map sensor for the ECU. They are straight through design, so as you can see, the fuel will go directly to the port. It looks a little bit obstructed from the top, but when you take a look to the port, there's no real obstruction. We've added some standoffs here and here around the studs, because it's different on the exhaust manifold as well. Now, to make these, I've looked at several options. My first idea was to have the CNC cut from a block of aluminium, but it was quite difficult because of the shape of the manifolds. I could slice these in different sections and then weld them back together, but still it was very expensive. Then I looked at sand casting, but this was quite expensive as well. It wasn't that bad, but I had to make a couple of dozen manifolds just to have our initial investment for our patterns back, and I don't think that that's really an option. I also looked at casting these myself, but again it would have cost me some time and some money to invest in all of the stuff. So I looked at casting these out of some heat resistant polyurethane, but in the end what I found and what I'm going to use is I'm going to 3D print these at home using my FDM 3D printer and a special filament. So the filament that I'm using is 3DK Top, which is a thermoplastic which can be cured in an oven after we've printed it, and then it will be stable up to 240 degrees, which is more than the highest temperature epoxy resin that I could find, so it will be tougher against temperature than a carbon fiber intake manifold. It's also quite rigid, it's quite stiff. All the walls of the manifolds are 4 millimeters, so it's quite strong. I can stand on one of these manifolds with my entire weight and it won't break, so that's not really an issue. We're going to do a small test to see if the thermoplastic is fuel resistant. The manufacturer says it isn't, and I have a solution for that, but we're going to do some tests. And I'm just going to make my set and we'll run it on the engine and see how well it works. There are some Formula Student teams that are using the 3D printed intake manifolds, and some have great success with it and some don't. So I'm happy to test this on my engine. If it doesn't work, we'll figure something out. Maybe we'll cast these ourselves in aluminium after all, or we may do with a carbon fiber aluminium hybrid. I've also thought about that by having the flanges water jet cut in aluminium and then making the runners out of carbon fiber. That's also an option, but again, the carbon fiber isn't as heat resistant as this thermoplastic. So I'm happy to try it. It's a great way to make one-off pieces without having a really large investment. Pure material wise, I think this costs about 50 to 100 euros for all of the material to go into these manifolds. Of course, it takes some machinery, it takes quite a lot of time, so it's not for free, but it's about 1/10 of the price to have these 3D printed in metal or having these sand cast. So we'll do some tests and we'll 3D print these and hopefully they'll turn out great. I've gone through quite a few prototypes to get these dimensions correct, to make sure that it fits without having any obstructions with the coolant tubes or the exhaust manifold. So yeah, I'm quite happy with how it turned out. Hopefully we'll be able to get some real manifolds on my engine quite soon. So I've done some test prints just to check things out. This is the bung with a 1/8 NPT thread to use as a vacuum pickup on the manifold, and this is a test piece for the flange, and it has a stainless riv nut in there. It's been countersunk, so it's nice in there. It's really strong, it won't come out. This is one of the older manifolds that I printed. As you can see, these are the bungs, so this should fit in there, and it has been threaded. This is a test piece for a flange here, so the nutsert will be in there because these threads will be loaded when the manifold is mounted to the engine and the throttle bodies are mounted to the manifold. These threads will take some load. This is threaded in there. It won't take much load. It just has a little hose going to an ECU sensor. One thing that we also need to do is to make sure that the thermoplastic that we're using is able to withstand the fuel in the intake manifold. Now the 3DK top filament isn't resistant to fuel as it is, so we're going to try to make it fuel resistant, and we're going to use this. This is Dictol, this is a capillary sealer, and this will completely soak into our 3D printed parts and fill everything with sealer, and normally it should be fuel resistant. So what we're going to do is we're going to coat one of these with the Dictol, and then we're going to soak them both in some fuel and see how they fare and if it's fuel resistant enough. But bear in mind that we're going to soak it in fuel, and the intake manifold has just need to withstand some vaporized fuel into the manifold and not completely standing fuel, but we'll see how it fares. So we're going to pour a little bit of the sealer in this glass jar, and we'll soak this one, or this one, we'll soak this one in. So we're going to put a little bit of the sealer in this glass jar and soak only this one in the sealer for 15 minutes. Once it's completely soaked in there, then we're going to let it dry, and then we're going to put it into some fuel, and we compare it with the untreated part and see how it goes. This is the part that has been coated in the Dictol. It doesn't really feel any different. It has been left to dry for a couple of hours. This is the uncoated part, so we're going to put this in the fuel. This has a really thin wall, so if anything starts dissolving, this one should go first. So we're going to put it in the fuel and we'll see how it fares. Well, everything has been here for over a week and I can see no real deterioration. I've checked it a couple of times during the week. We'll take it out now. There's no difference whatsoever. There's no deterioration. It's still solid. It hasn't gone soft. The threads on the inside are still perfect on both pieces. So this one has been coated with the Dictol and this one hasn't, but there's no difference at all. Now I have the coating, so I will use it, but as you can see, we don't have to worry about any fuel spray inside of the manifold, because if it can withstand more than 100 hours being submerged in fuel and there's completely no deterioration, I don't really have to worry. So this test is quite successful. So now I'm going to completely finalize the intake manifold design and we'll print it. So I was trying to 3D print the intake manifold and it went a little bit wrong. You can see it turned and it's not stable, and that's because the bottom has warped, and this has warped a lot. As you can see, it's completely crooked. This is the first time that this has happened to me, but this is also the first time that I'm printing this large footprint object in completely 100% infill, so it's completely solid, and this has caused a little bit of shrinkage. Now I'm going to try again. I'm going to fix this by putting the print bed on a higher temperature. I'm also going to build an enclosure to keep the warping a little bit at bay, but it's very strong, so I'm not really doubting that it won't work. As you can see, it's nice and smooth inside. It's really strong, I can't break it. So I'm just going to put this to the side, build my improvements to the 3D printer, and I'm going to try again. I've printed the first of the intake manifolds. After my first fiasco, I changed some settings. So now I'm printing on a hotter bed surface. So it's 90 degrees centigrade instead of 60 degrees centigrade. Also, I've changed from using 100% infill to 50% cubic infill, and I'm using 2mm walls, so in strength it doesn't change too much, but it uses a little bit less filament and there's a little bit less warping. Also, as you can see, I've built an enclosure, and I've used some of these foam floor tiles just to enclose the printer a bit, to keep the temperature a bit more stable in here, so that there aren't too many temperature fluctuations. And I've printed the first one. Now I'm going to print the other one, and it's just the same, and just mirrored. So the bed is preheating at the moment, about 50 degrees centigrade. I always clean the print bed using some of this solvent-based cleaner. I've re-leveled the print bed before the last print, so that should be okay. There's another difference that I'm doing, is I'm using a 0.25mm layer height, but I'm using for the first layer some very thin layer widths, and everything's nice and smooth. But I may need to sand down the mounting surfaces to make it completely flat, so it will seal nice. On this one it's not really a problem. This one it might be a little bit of an issue because it has been printed at an angle. So now it's preheating. I have my SD card here. We'll pop it in. I'm going to close up the printer and then preheat a little bit more, because it will preheat a lot quicker when it's not exposed to the environment as much. The entire print time for one of these manifolds is 15 hours and 20 minutes, so it's running all day. I have left the supports on there because this will have to be annealed or tempered in an oven, but I'm going to do this once the second one has always been printed as well. Both of the intake manifolds have been printed with 3DK top filament. There wasn't any warping this time, so both manifolds are completely printed. You can see that I left the support material on there, and that's because we need to do some post-processing. I have the instructions here from 3DK, and we have to post-process this. This is like a sintering step, to put them in a normal convection oven at 110 degrees centigrade, and we have to leave them in for, it all depends a bit on the wall thickness. So this is a very big object with heavy walls, so we're going to leave this in for a couple of hours. We're preheating the oven now. Once it has reached the 110 degrees centigrade, we're going to place these in. Once that we think that it has post-processed enough, then we can turn off the convection oven, but we have to leave these in so that it will gradually cool down without having a heat shock. Once the post-processing has been completed, then we can remove all the support material, and then afterwards we can do all our little machining bits that we still need to do. So now I've just put them in the oven. I've set the timer to about 3 hours. We'll take a look if that's enough. Hopefully everything will be completely post-processed. We really want the heat to get in there all the way. While it's post-processing, it will completely shrink 1% in all the directions, and that's the reason why we had to print it at 101% to compensate for the shrinkage. So we'll leave this in there, and hopefully 3 hours will be enough. I've done the post-processing on the 3D prints, so now I'm just going to remove all the supports. I removed all the support material from these intake manifolds, and all is well, except for one thing, and something really annoying. This flange plate was really straight when I took it off of the printer, but when we're doing the post-processing, I've put these in my oven on one of the plates that was included. What I didn't know is that the plate was bent a little bit from the heat that I've used when cooking, and both these flange surfaces have warped a little bit because once the first time it gets soft, it sags a little bit, and it just sagged to the shape of the plate. When I use my ruler, you can see that it's not completely smooth, not completely flat anymore. So we'll have to remedy this. I had to do it the same on the top surface anyway, so we're probably just going to refinish this on like a bench sander. But that's it for now. We're going to reshape this to make sure that it's flat again. These surfaces are pretty okay. It's just not really smooth because of the ridges. It's been printed at an angle, but this is really annoying. So I'm hoping that I don't have to remove too much of the material. The solid thickness of this flange is 2 millimeters, so I can remove a bit if I want. I'll have to be careful. Now it's pretty good. The only thing that I need to do is I need to put the inserts in for the studs, and I have to tap these holes for the vacuum tubing that goes to the map sensor. Well, all in all, I'm pretty happy with this. Now once I've done all of the machining and the tapping, then we can use the Dictol to treat this, to get this completely fuel resistant. And then we can test fit it on the engine. So I'm hoping that it's all okay. These are our intake manifolds that we 3D printed. There are a couple of things that we need to do before we can coat these in the Dictol capillary fluid. And one of the things is that we have to lineage the mounting surfaces. You can hear that there are really small ridges in there, and that's just the layers of the 3D printing. On the top we have the layers, and on the bottom the surface was completely flat, but it has warped a little bit when we put it in the oven. So we have to lineage these surfaces to make them completely flat. I already did this on these manifolds, and I used a belt sander to do that on a relatively low grit sandpaper, and a little bit of pressure just to make these surfaces flat, so that they will be able to mount really well to the throttle bodies. Now I have to do the same on these. The second thing that we need to do is we need to tap these holes to fit our vacuum fitting. These will have to screw in here, and that's to take a vacuum signal for our ECU to help with engine mapping. So we'll start off by lineaging the mounting surfaces, and then we'll tap the hole for the fittings. This is the belt sander that we're using. It's 120 grit sandpaper, and it's quite cheap. It's about 50 euros. And we're going to use this. I had to straighten the bed a little bit because it was warped from cheap construction in China, and this wasn't completely flat, so I had to redo it again. So I'm going to put the sander on, and we're going to put the flange on here, and we're going to move a little bit, and we're going to check frequently, not putting too much pressure on there, but just enough to make sure that it will be straight. I'm not sure if you can see it, but the layers are gone, so it feels really smooth. We can take our straight edge to check for straightness in all directions. And that's perfect. So now, because it's a plastic, there's a lot of dust and a little bit of fraying on the edges. We're going to take a sharp knife. We're just going to go around the edges, removing the fraying. So that's this flange already done. Now we have to do the larger one. Now we have to do quite a bit of material removal on this one. So now I'm really close. You can see I put the ruler on just a really tiny bit of play, but not much. I grounded a little bit in this direction just to lower the center, because that's where it was a little bit high. And then I flattened it, so we're really close. I'd like to try to see if we have no low spots, just using permanent marker. I'm going to color the flange surface in. See, it's really smooth. Now I have to double check if it's flat, and it is. So no movement at all. Completely flat across the flange. Now we have to tap these holes to fit these barbs for a vacuum hose. The reason that we want to do this is we want to have a separate vacuum signal from all of the runners individually. Then it will go to a plenum, and from there it will go to the ECU to get a map signal. So now we're going to tap these holes. I already did this manifold, so we have to do the same on that one. So we're going to put this in the vise, and we'll prop it up like this, that it's quite sturdy. So now we have to drill these out. We have to drill these holes out. The tapping drill for a 1/8 MPT fitting is 8.7 millimeters. However, I don't have that, so this is an 8.5. We'll chamfer the edges to get the tap started a little bit. Now, with the last ones, I couldn't get the tap started on an 8.5, which I have been able to do in the past. So we're going to enlarge the hole to a 9mm. Which is a little bit too big, but it works. So now, because this is plastic, we have to be a little bit careful not to strip the threads, otherwise our complete manifold is junk. So we have to put quite a bit of pressure on there to keep it in for the first few threads, and then once it sticks, then we can thread it in. So I have a fitting here. You can see that once the top few threads are starting, we can get it. However, it's crooked at the moment, but we can correct that a little bit. But we have to be really careful not to strip it. I found that tapping things on 3D printed stuff is quite difficult. On the test pieces that I did, it was actually quite easy. I'm not sure why it's struggling again. All in all, it went quite well. On this manifold, the holes were tapped without any problems. You saw me tap the first one on this manifold, which took a little bit of finessing to get it okay, but it's good. The last one, this had a problem which I was dreading, and it cracked because of the pressure of the tapered tap. While I drilled the hole a little bit bigger, it still had too much pressure, and there's a little crack on the outside here on the edge of the standoff until about here on the outside of the manifold. It doesn't go completely to the inside. Now I already told you I was maybe contemplating to epoxy the inserts into the manifold, and now I'm definitely going to do that just to keep this together, to make it stronger. Our sealant will penetrate the crack and will seal that up. That's not really a problem. Because the crack's only on the outside, I don't really think it will cause any strength issues. But now we need to make room for the threaded inserts for the studs that hold the throttle bodies to the manifolds. So we're going to rig this up to put this in drill press, because we want to get the holes completely perpendicular to the mounting surface, and then we can install the threaded inserts after we've sealed the manifolds with the Dictol sealer. Okay, so we're trying to drill out the holes for the threaded insert for the studs. This is an angle gauge, an angle finder. It's zeroed now. You can see that it's zeroed on the manifold. Now it's quite difficult to clamp this. You can see how it's on there, so I have to keep it steady while I'm drilling in this angle. So I'm going to put the camera on a stand and try to drill it. We're drilling the holes to 11mm for the threaded inserts. Now we drilled all the 4 holes for the threaded inserts, so they fit. However, they have a little countersink head, so we need to countersink the holes to make sure that they fit. Okay, so I've done all of the machining that we need to do on the intake manifolds. Now we're going to coat this in Dictol. It's a capillary sealer, so it will flow into all of the crevices and it will bond and protect it in there. Now we have to soak this for 20 minutes. first manifold has been dipped in the Dictol for 20 minutes. So now I've hung it out to dry. I've put the second one in and I've put some tape around the back to take up the room. And now it's completely submerged, and we'll leave this for 20 minutes as well. Then we'll take it out, let it dry like the other one, and we'll put the Dictol back in the can because we can reuse it as much as we want, except the amount that's been penetrated into the manifolds. But it looks quite okay. Normally it doesn't really change much. This has maybe penetrated the sanded surfaces a little bit, so it has a little bit of a darker color. But the most important part is that it will fill any voids, it will make it completely resistant to fuel, and make it also a bit stronger. So we'll leave it in there for a bit longer. The manifolds have dried, and now we're going to install the threaded barbs, which we can screw in like this. This already has been tapped. Now on this one there's a little crack here. We're going to glue this with a bit of epoxy on the outside, and we're also going to epoxy the threaded inserts in there. I'm going to glue on here and thread the barbs in the other one, and I'm going to let this dry before I'm going to put the barbs in this one. Just using some clear epoxy. So now we're going to get some epoxy and we're going to put it on the threads. And we'll thread it in. I'm just going to put it hand tight, like so, and we'll let this set. I've installed 3 of the 4 inserts. The top ones are on there, and this one needs to be tightened. So it's a stainless countersink nut insert. So we'll thread our installer tool on. What I like to do is just press it in to make sure the countersink is in its position. And now we only want to tighten this a little bit. Like this. And now it should be on here. As you can see, these are stainless threaded inserts, and the epoxy on our barb fittings has dried. So this is one side of the manifold that's ready to install. We're going to install the barb on this one and position the inserts, and then we can test fit them on the engine in our chassis. I've mounted the 3D printed intake manifolds to the head to do a mock-up, and everything seems to be okay, except that I made a small error, and that's the mounting holes for the studs were 3D printed in the correct positions, but when drilling out for the metal inserts I made a slight error and the drill shifted a little bit, and therefore the M8 studs, which are a really tight fit, have moved a really tiny amount, and I cannot get them all into the throttle bodies, so we're going to try and fix it now. You can see that at the moment only these two studs are in position and these line up. I'm not sure if you can see this, but the inserts on this and this are moved a little bit towards the center, and therefore they do not line up when these are in position, and that's because while the holes were completely in the correct position, I had to drill them out a really tiny amount to get the inserts in, to make it sure that it was a correct fit. However, because all of them shifted a really tiny amount, the end result is that they do not fit completely, and I'm trying to figure out a solution without having to make completely new manifolds. So we're going to take this off and try to see if we can find a solution. My brilliant solution for fixing this without having to make completely new manifolds is easy but a little bit of a faff. So we have the M8 threaded inserts, and now these are M6 studs, and the silver part is an M8 to M6 reducer, which I can screw in like so. So now we have a little bit of movement in there, but we're going to Loctite these in so that they won't come out. And the good part is that it fits. So I'll put the throttle bodies onto the manifolds. The thread reducers really did the trick. It works. It just needs a little bit of Loctite just to tighten them up a little bit and to make installing it a little bit easier. But it's all bolted on. It's really sturdy. I'm putting quite a bit of strength on there, and it's not moving. It clears the exhaust manifold like a charm. The throttle cable on my setup is in the center, and this clears as well. There's quite a lot of room in there, even for a heat shield. However, this is a mock-up manifold which will be for sale if anyone wants it, because I have a Zircotech ceramic coated manifold to go on. So this works. What we're going to do now is we're going to install the back shield for our air filter, which is an ITG sausage filter. It's a foam filter which will go on like this. I already measured and marked the back plate, so I just need to drill the holes for the trumpets, which I'll do now, and then we'll be able to mount this and to see if everything clears. Normally it will fit in right between the coolant tube and the back plate here. I've got the holes for mounting the air filter, And the only thing that I'm still thinking about is the position of our intake air temperature sensor. It will be either there or there, but I'm going to mount this on the throttle bodies and then we're going to take a look. The AT power throttle bodies have a really nice system for removing the trumpets. They're all threaded, so no bolts that need to be undone. You can just screw them off like this. These have tapered runners. This is an option. You can have them with straight runners or tapered, so these are a little bit wider here than they are at the base. You can really spec these as you want them. I've chosen for a center throttle cable, which is a bit of a cleaner look, but with some hindsight it would have been easier with a throttle on this side, because it will clear the manifold a bit easier. Now let's hope that I've measured this all correctly. Okay, so you can see this is a really nice backplate. It's an ITG backplate. There are also some gaskets in between. For the more popular applications, you can buy these backplates with the holes already cut in. But of course, this being a custom application, there are special wrenches available which will fit on here, so you can torque them. I don't have it. I don't think it's really necessary. Okay, so you can see our throttle bodies with our backplate and our exhaust manifold, and now it will just clip on. The foam filter element clips on using a flange at the bottom and these tooth fasteners on the top. As you can see, it will clear the coolant tube. It hits it a little bit, as you can see, but not really an issue. The difficult thing is that the position of the coolant tube prevents it from easy removal of the air filter, which is a bit of a bummer. Fortunately, because we have all the silicone couplers, there's a little bit of flex in there. We can move it a little bit if we need to, but that's a bit of an issue. I've looked for a different air filter that would clear a little bit easier, but this is a really shallow profile, and because of the spacing between the carbs is really small, some two separate filter elements didn't clear at all, and I didn't want to run the open throttle bodies because all of the dirt that would get in there. It looks a little bit less blingy like this, but it's great. With our valve cover installed, it looks really nice indeed, so I'm really happy how it turned out. I'm not really worried about the intake manifolds. It will stand up to the heat, I'm pretty sure of that. It's more heat resistant than any high strength, high temperature epoxy for carbon fiber. So if carbon fiber manifolds will hold up, these will too. Only thing that's a little bit wait and see is how well they'll deal the vibrations of an engine. However, they're really strong. If I'm jiggling this like jiggling them like this, I'm hearing everything else rattle, but not the manifolds, no cracking. So it looks really nice. So I think we can round up this video. The next time that you'll see the manifolds are when I'm mocking up the car or when I'm running the engine. So I'm happy how they turned out. Hopefully it will work, but I'm pretty confident. The only shame is that with the air filter on, you cannot see the open bell mouth and the moving of the throttle plates, which are really cool. But it will be way healthier for the engine with an air filter on there. Hopefully you'll enjoyed this video, and don't forget to subscribe so you won't miss any of the upcoming videos, and I'll see you back on the next video. Goodbye!